Hello everyone. Today I will be presenting two recent projects that we have been working on in our group using blue water. But before going into the physical and technical details, I would like to give an overview about how we are using blue water. So we use blue water to perform multi-scale simulation and to study multi-physics systems, such as developing force field parameters for fluid interaction with 2D material, studying the biological molecules interaction in nanopores, also proton transport and perovskite material. Also, we develop machine learning tools to reduce the computational cost of molecular dynamic simulation, such as mapping all atoms to coarse-grained approximation using deep learning. And more recently, we have been working on studying DNA interaction with the crumple graphene. With these different physics, we require using different software. Here, we show brief software for what we are using, ranging from quantum software to molecular dynamic and up to continuum softwares. And with these different softwares, we require resources to do high computational performance, where blue water allowed us to achieve these goals. And as an example of performance, and for sake of time, I'm showing here only the scaling of NAMD for our codes in a blue water, where we can achieve 90% of the ideal performance. Now, with this overview, I will jump now to talk about our two projects for today. So in the first part, I will be talking about new power scaling and the relation between the ionic conductance and the ion concentration, which is related for the high velocity in carbon nanotube, CNT. And then in the second part, I will focus more about the velocity inside the carbon nanotube, where I will be discussing the thickness dependence of fluidic transport in nanopores and nanochannels. So let's begin with the first part. So ionic transport can be found in different applications, such as biological channels, water desalination, and nanopower generation. So to cause the flow of ions within this system, we apply either concentration gradient or potential bias through the nanofluid system. And when ions flows through the carbon nanotube, it will generate ionic current, which is associated with multi-physics phenomena, such as diffusion and migration of ions, electroosmotic flow, surface charge regulation, depending on the chemistry of the nanofluidic system, and the confinement effects. Now, the ionic currents will be reduced for sure. Ionic conductance, where we are interested in studying the ionic conductance in this carbon nanotube. Experimentally and from computational point of view as well, theoretical relation has shown the relation between conductance and concentration obey power law with exponent alpha. Alpha is the scaling of this relation, which is the value of alpha depends actually on the physics of the system, and it has been found to be one for the bulk system, where we have like a bulk and we don't have fluidic transport, meaning we have large system, and 0 when we have very high surface charge causing saturation of the nanofluidic transport. And also 1/3 or half, depending on the amount of surface charge. More recently, our experimental collaborator, they found the value could be 2/3. And we tried to help them to explain the reasons and the physics with this observation. And we were thinking the 2/3 comes from the half with enhancement due to the high velocity of the ionic transport within the carbon nanotube. So to explain this, we needed a computational tool where we can turn off the effect of the velocity of these ions and then turn it on and see how the ionic conductance will change. So to achieve that, continuum approximation with coupled Poisson-Nernst-Planck with Navier-Stokes is a tool where we can achieve this goal by turning off the velocity and turning on the velocity and study how this ionic conductance will change. So with Poisson-Nernst-Planck equation, we can study the ionic flux, transport of species, and the electric potential, where Navier-Stokes help us to study the velocity and the pressure field within the carbon nanotube. And if we solve only the PNP part, Poisson-Nernst-Planck, we don't include the effect of the velocity, and we can then turn on again the Navier-Stokes part and see how the velocity will change. We coded this equation in OpenFOAM, and we use unstructured mesh with axisymmetric geometry to describe our system, and high-resolution mesh with, inside the CNT, and we started our simulations. So first, we consider a carbon nanotube with diameter 14 nanometer and length 10 nanometer. And when we solve using only the PNP part with ignoring the velocity effect, we found alpha is very close to be half. And when we turn on the velocity effect, we found alpha to be 0.62, which is very close to 2/3. And with this simulation, we explained the experimental measurement where the high electroosmotic velocity causing this enhancement of the ionic conductance. But this value of the conductance depends on the surface charge, and experimentally it's very hard. It's very hard to measure the surface charge or to know the surface charge. And there is like a lot of theoretical relation, but this relation does not count for the electroosmotic velocity. So we decided to go with the experimental geometry, diameter 1.5 nanometer and length 10 nanometer, to find the surface charge by taking their conductance measurement and try to iterate our solver, and we fit their data to find the surface charge. But here we have a problem, is continuum is not accurate for scales less than 10 nanometer. So what we did here, we coupled molecular dynamic with the continuum to correct the continuum approximation and to find more accurate result. And with this, we found the surface charge to be between minus 15 millicoulomb per meter square up to minus 75 millicoulomb per meter square, depending on the pH of the system. To cross-validate our continuum accuracy with the experimental, so we calculated the selectivity coefficient, which is the ratio of the current produced by the cations to the ratio of the current that produced with anions. We found it within the simulation to be 3.7, where in the experimental it was 3.9, which shows very good agreement. Now, we wanted to go further, and we wanted to focus from molecular point of view on the couple and the movement between ion and the water, and what is to just like make sure what we observe in the continuum of high electroosmotic velocity is accurate. So we run molecular dynamic simulation, and we can see in this slide we are tracing two ions with several water molecules within the CNT over 3 nanosecond time. Here we have the trajectory, and we can see the blue trajectory of the ions, where the red trajectory are for the water, and there is certainly coupling in the movement between the water and the ions within the CNT, which suggests high electroosmotic velocity. We wanted to do a further study by changing the surface charge and see how it does affect the electroosmotic velocity, and we found at the low and moderate surface charge, the velocity of the water and the ion is almost the same, but when we go for very high surface charge, the velocity drop for both the water and the ion as well. With this slide, I would like to turn the gears and go to talk more about the velocity in nanofluidic systems. So in fluid dynamic and pipes, we usually express the mass, the flow rate within the pipe based on the pressure difference within Hagen-Bosse equation. But in nanoscale, this equation has shown a high underestimation from both experimental and computational result data. And from there, we were thinking about ways to improve this equation to validate it for nanoscales. And one way we were thinking about is if we take the confinement effect within the carbon nanotube and how it does change the physical properties such as the viscosity mu here, we can enhance this equation by considering the changes of the viscosity based on the based on the radius and the length of the carbon nanotube. As well, the friction coefficient, where at nanoscale fluid system, we experience high slip phenomena within our systems. So what we did here, we took the Hagen-Bousset equation with bulk properties, and we plotted here with the black line, and then we took it with varying only viscosity with the green line, and we took it with varying the viscosity and the friction coefficient, and we cross-validate that with different sizes of carbon nanotube, and the blue colors here is our molecular dynamic simulation, and we can see there is a good agreement between our suggested correction for the Hagen-Bousset and the simulation. But we wanted to go further, and we took from literature several experimental data, and we normalized that with the flow rate that we can calculate within Hagen-Bousset equation. We name it as enhancement factor, and we can see the ratio can go for 1,000. But when we apply our corrected Hagen-Bousset approximation, we can see the enhancement factor goes to 1, which suggests the good accuracy of our approach within correcting the Hagen-Bousset equation. From there, I would like to conclude my talk. I have talked about a new scaling the power relation and ionic conductance concentration relation, and how we corrected the continuum approximation using molecular dynamic. We also, I also talked about correcting Hagen-Bousset equation and how our enhancement factor approaches unity with fitting the viscosity and varying the friction coefficient. At the end, I would like to thank Professor Alex Noy, who provided us with the experimental data for the ionic conductance concentration project, and special thank for Blue Water and their team. Last year, we used around 600,000 node hours. This year, till now, 70,000. Without Blue Water, this project was like impossible to complete. Thank you very much.